Alright guys, I'm going to be solving the test that we took before spring break. This one will cover problems 1 and 2. Alright, for the first one is a series of true, false, fill in the blank and free response questions. First one asks true, false, every linear program has a dual linear program. The answer to that is true. Not too much explanation here, but you could think that you can either turn every linear program into a normal minimize or a normal maximize problem, and then the dual of that will be just the vice versa, either a normal max or a normal min. The second one that says complementary slackness tells us that if a constraint is slack in the primal LP, the associated constraint in the dual LP is binding. Okay, so a couple of different sort of thought processes that would lead you to the conclusion that this is false. For me, it's this, that constraints in the primal, so let me call this constraints in the primal, are associated with variables in the dual. Okay, so constraints in the primal are associated with variables in the dual. This statement says that the constraint in the primal is associated with a constraint in the dual, so that's automatically false. Okay, that's sort of how I think of it. You could also have just known more exactly what the definition of complementary slackness was. Next one says true or false, primal LP is unbounded, then the dual LP is degenerate. That's also false, and the dual LP would be infeasible. Okay. Next one, fill in the blank. Given a basis, the basic variable values can be computed by the formula. Again, all I was looking for here was B inverse B. Okay, that's the formula in a sense that we have given a tableau that represents sort of all the problem information for a given basis. The part of the basis that represents the basic variable values is B inverse B. Next one, the theorem which guarantees the optimal solution to the primal and dual LPs are in fact the same was called strong duality. Okay, now people may be not too happy because if you just said duality, that's not going to cut it, because of course we had two theorems about duality, weak and strong duality, and strong duality is the answer to this one. Next we get to free response. First it says explain why the primal or dual LP might be easier to solve. Okay, what I was trying to get at here was this. So let me write, this is going to be my answer to part 6. If we have a primal problem, we have an A matrix that, let's say it's of dimensions m by n. And if we have, that means that the associated dual problem is going to have an A matrix that's n by m. Specifically, the A matrix in the dual will just be the transpose of the A matrix in the primal. That means for the primal and the dual, in order to compute a B inverse, in the primal this is going to be of order of magnitude m by m, and in the dual this is going to be of order of magnitude, n by n. Okay, because the size of the B matrix is related to the number of constraints or the number of rows in the same matrix. And we talked about in class that this inverting a matrix is one of the most computationally expensive sort of operations, if you'll say, that a computer can do. So depending on the size of these different B matrices, one of these might be significantly easier to solve. And that's what I was going for in this question. So you would have written something about that. And the last one for number 1 says explain how to check for dual feasibility in the primal simplex tableau. Okay, and we went through and sort of derived that in class, but let me write the answer over here by 7. What we said was that to check for dual feasibility in the primal tableau, all we need to look at is the reduced cost of our non-basic variables, okay, which are these. And we said for a maximized problem, we want those to be all non-negative. For a minimized problem, we wanted those to be all non-positive. And that was the exact same criteria that we used for optimality in our simplex method. Okay, so those were the answers to 1. Now we get to 2, And the first thing it says to do is write the dual of this LP. Okay, so again, the way I do that is I say, okay, there's going to be a dual variable associated with each constraint in the primal. I'm going to call them y1 through y3. And I know the decision variables in the primal are x and y. It really doesn't matter what you use to denote the decision variables in the dual, as long as you don't use x and y, because we can't have decision variables in the primal represented by the same variables in the dual. Okay, so the dual of a max is a min, and then what I found in my right hand side is now going to become my objective function coefficients. So 6y1 plus 2y2 plus y3. Okay, I had two decision variables in the primal, which means I'm going to have two constraints in the dual, and the right hand sides of those constraints are going to be found by looking in the objective function of the primal. So what I mean is I'm going to have 1 and 3 over here. The types of those constraints in the dual are determined by the types of decision variables in the primal. Since both my decision variables are unrestricted in sign, that means that both my constraints in the dual are going to be equal to constraints. So I'll go ahead and write those. The next step I usually do is to write out the A matrix in the dual. It's just the transpose of what we found in the primal. So what was my first column in the primal is now my first row in the dual. So negative 2y1 plus 2y2 plus y3. Now my second column from the primal is my second row in the dual. 3y1 minus 2y2 plus y3. Okay, almost done. We just need to write out the types of variables for the dual, and those are going to be determined by the types of constraints in the primal. Okay, so the variable type of y1 is determined by this constraint type. A less than or equal to constraint for a maximized problem is a normal constraint. So that means y1 is going to be a normal decision variable, which is non-negative. Similarly, y2, less than or equal to constraint for a maximized problem, is a normal constraint, means we're going to have a normal decision variable. Finally, y3 has an equal to constraint, which means it is going to be an unrestricted and signed variable in the dual. Sorry, y3. Okay, and that would have been the answer to the first part. Let me scoot the page up. The second part now says, if the optimal basis of the primal LP, which does not produce a degenerate solution, consists of the variables x, y, and s2, which of the dual variables are guaranteed to be 0? Okay, so this was intended to be, fairly easy. You could have actually solved it in a more complicated way, but a couple of things. The optimal basis and not degenerate means this, that x, y, and s2 are all not equal to 0. Okay, because if one of them were equal to 0, then this would be a degenerate solution. Okay, so we know they're not equal to 0. And then the other part of this problem was to use your knowledge of complementary slackness. Complementary slackness said for each constraint, the slack in the constraint times the associated dual variable, or the shadow price. You can think of it either way. The product of those two is 0, okay, for each constraint. So basically, which of the dual variables are guaranteed to be 0? We know the slack S2 of the second constraint is not 0. So we know S2 is not equal to 0. But we know that Y2, which is what we call the shadow price, or the dual variable associated with the second constraint, back here when I wrote the dual, Y2 was that shadow price or dual variable. I know the product of those is equal to 0. So if S2 is not 0 times Y2 is 0, that means Y2 is equal to 0. Okay, sorry, let me scoot it up. Okay, so that was just using what we knew about complementary slackness. That's the only dual variable that's guaranteed to be 0. Okay, so that was the answer, just Y2. You could have actually solved this problem by computing CB B inverse, which we know from our optimal tableau, these are the shadow prices for a max problem. Okay, and if you actually went through and computed CB B inverse, would have been a lot harder, but you would have gotten that the shadow prices equal, let's see, 0.4, 0, 1.8. So again, which of the dual variables are 0? Would have been the second dual variable, which is y2. And that's how you solve the second one, and I'll solve the rest of the problems on a different video.